Okay, so Thevenin and Norton theorems, or Thevenin and Norton equivalent, as we will see. So Thevenin and Norton equivalent circuits. Before we get into what Thevenin and Norton are about, we need to do a little bit on source transformation. So all that means is you're going to change your voltage into a current. It also changes the shape, series to parallel, parallel to series. That's it. It's not that big a deal. So we have, say, source transformation first. Source transformation. And all that says is that you can go from a voltage source, Vs, in series with a resistor R, put a little end cap on that, just to signify that it could go on. And all that means is you can interchange between that and a current source, Is, in parallel with a resistor R. So we have here two circuits, two portions of a circuit, where the resistance is the same. We have the voltage Vs there, current source Is there. And we can say that Vs, the value of the voltage source on this part of this, on this sort of version of the circuit, is equal to Is, the value of the current source on this version, times R. Yeah, it looks like Ohm's law. All right, so how do we get there? We can kind of prove this. It's not too hard. So one option is we can say either we leave them open like this, or we close them. So if we look at them open first, we say open, that's as drawn. If we have them open, we want these to be the same, right? We want these things on the ends to be exactly the same from this version to that version. We're just transforming the source is all we're doing. So if we leave it open, meaning we don't connect anything from there to there, we can call this end A and this B, and this is A and B, and this is all connected to whatever other stuff in between there. Same as that. We could say that there's some voltage VAB. So there's some plus, minus, there's some voltage VAB, and there's some voltage VAB here. The voltage of A relative to B, VAB. When they're open and you're on this side, they're open, that means there's no current flowing, which means that the voltage at A relative to B is just Vs, right? We saw that before. So that's just going to be VAB is equal to Vs. When you're on this side, the voltage across A and B here is the voltage across the R. Well, the voltage across the R be V across the resistor R is equal to however much current is going through there, which since this isn't closed, it's just going in a loop like this, which means that that current is just Is times the resistance, which is R. Well, that's ISR, and remember we'd said this, therefore that is just VS. So it's the same. Oh, that was VAB. We said that, but we didn't write it. Okay, closed then. This is important. Closed. This will come up again when we talk about Norton theorem. It's easy to forget this bit. When we close it, what we want to do is we want to really just close it with a wire. So if I draw it again here a little small so that we can kind of remind ourselves what we're talking about. Have the resistor. Shoop, close it with a wire. When we close it with a wire, the voltage from here to here is the same, right? Because there's no element in between there, so the voltage is the same. Okay, so we can talk about the current though. Since this is the positive terminal on top, negative's on the bottom, the current's going to be going clockwise. So it goes down here. Let's call it I for now. The current through there on this form of the circuit will be I equals Vs by R. If we do the same thing on the other form that had the current source, have Is R there we go. So once we close this up with a wire, the current is going to go like this, up, over, 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 over. It's going to bypass this resistor because it would much rather go through just the wire. So this will be I equals Is. So what we see then is that in order for this version to be equal to this version, when I say equal, I mean be the same, then we have to have that the voltage here on the current source part has to be equal to Vs. And there we see this showing up. There's that. And we need to have that the current through this wire be the same as the current through that wire. Well, the only way to have that is for Is to be equal to Vs over R, which is just the rearrangement of Ohm's law there. So what we see then is that if we are to do this, then we require that this relationship be true. Okay, that's kind of the order that we do that in. And it turns out that you can do that too anyway. So everyone is happy. So this is source transformation. Before we do an example, I just want to mention what is Thevenin and Norton theorem then, because they're extremely related to each other. So Thevenin and Norton oops. I wrote the D before the A and the N and there. And Norton theorems. It's technically two different ones, though I don't know why. Basically, any linear circuit, let me make sure I read this right, any linear circuit can be turned into an equivalent circuit like this. That's what I wrote down. Let me do this. There we go. Any linear circuit, and as you know, that's all we're dealing in. Any linear circuit can be turned into an equivalent circuit, like this. So I'm saying like this because picture is worth 1,000 words here for this. I don't want to describe a circuit in words, and it's a pain in the butt. Basically, we want to say we have a box. And inside of our box is a linear circuit. Doesn't matter what it is. It's any old mishmash of all sorts of stuff connected together. It doesn't matter what it is at all. All that matters is it is linear. We have two terminals coming out of there. We're going to call them A and B. And we can turn that, there we go, that worked out okay. We can turn that into two different kinds of circuits. We can go voltage source, resistor as A, as B, And as we just saw, since we can turn a voltage source in series with the resistor into a current source in parallel with that same resistor, then if we can do this, we ought to be able to do this. And I suppose you can do whichever one your heart desires. Doesn't matter to me, since they are equivalent. Those resistors are going to be equivalent, of course, because of source transformation. The voltage, we'll call it VTH, and the current source, we will call it IN. And so here, put a dotted box, is what we have done to the linear circuit. So the linear circuit was in this solid box with A and B coming out. We've replaced everything inside of this box with just the stuff inside of the dotted blobs. Okay, so you have two options. You can do a series thing with voltage and resistor. That's my favorite way. It's just easier in my head. It seems easier. Some people might prefer this one. However you want to do it. It's good to know both, as we'll see. It's very useful to be able to do both. Sometimes an analysis might be easier with something in parallel, so you go ahead and turn it into this. Sometimes it might be easier if something's in series, so you go ahead and do this. It's definitely good to know both. This one is Thevenin. This one is Norton. Now, I think Thevenin did his first, and then Norton did one, which is a little weird because, as we saw, they're kind of the same thing. So it seems like someone was just kind of, I don't know, cheating. But anyway, they're related by source transformation. We'll make a note of that just so we can say that we've written it down. Related by source transformation. Now, oftentimes you'll see the R, you'll see it with a TH on there when it's Thevenin and a little N when it's Norton, but keep in mind that they're exactly equal because by source transformation, they're the same. So however you want to note that, doesn't really matter. And then of course we also have that VTH is equal to IN times R, and then whichever THN, whichever one you want to put down there, it doesn't really matter. So then we have that as well. Okay, and that's all Thevenin and Norton theorem are. You could go through a process and prove that. You can do that. It's not worth it, honestly. Normally I'm kind of a fan of proving things, but in this case it's genuinely not worth it. It's more or less the same as doing this. You just make a linear equation out of the stuff that's in there. It's not worth doing. What is worth doing, though, is an example. So let's do that. Page 3. Do an example here. And do an example. And then we will do lots and lots and lots of examples in subsequent lessons and videos here. Having a little bit of a drink there. Okay, so what we want to do is we want to use source transformation to find either the Norton or Thevenin equivalent circuit of the following circuit. So we have a resistor, another one, voltage source. We're going to do this. And I'm going to draw it like that. So we're going to say this is a 15. What did I write? 15. Almost looked like there was a decimal point there. There is not. It's 15 ohms, 10 volts there, 5 ohms here, and 3 there. We're going to put our terminal ends there. So this is our linear circuit. Linear circuit was a box, A and B. Linear circuit here. So this would be like A, B, if you want. And we want to make it into this and this. So let's do that. I haven't shown you how to do that yet, so the only option we have is to do a bunch of source transformation. So we'll see what happens. And we'll kind of talk through it as we do that. The first thing we see is, okay, we have a resistor here. It's kind of all on its own, really. It's connected to a node here, but to just one of the terminal ends there, so it's not really doing anything. Then we have this 15 ohm, and that's in parallel with this voltage source and 5 ohm resistor, right? They're connected across the same node, so that's in parallel there with those two things. So, let me go back to my little doodle here, and slide it over. If we can change this thing here that's in series, if we could make the resistor here be parallel to this one, then we could add them up. Right now you can't add them up, right? Because there's this voltage source there, so you can't add this 15 and 5. They're neither series nor parallel. So let me show you how we do that. Until you get used to kind of visualizing this, the best way to do it, again, until you get better at visualizing this, you don't need to do it all the time, and push yourself to not need to. Draw little endpoints to the nodes you're going to do, just so that way you can focus on them. Copy the whole rest of the circuit down. What we're going to do is we're going to make this voltage and resistor that are in series, we're going to make it into a current source and a resistor that are parallel to each other. So we have this 3 and that end. Then we have this 15 and that end. So that's everything but this. Now, since these are in series, we can make them into parallel. So I'll draw the arrow here in just a second. I want to talk about the arrow. So I kind of made them squiggly lines like this, curved lines, because it kind of helps you see it as like a line, and then it's kind of like this series, and then you expand it out to make it parallel. That's kind of how you can view it. All right, you like close it up, now it's series. You're gonna kind of, like you're opening a chip bag, right? You're opening a bag. Now you're opening the bag, now they're parallel to each other. And then of course you can rearrange the circuit if you want, square everything up nice and right angles if you're into that. But we can see now, node, down this path, resistor, resistor. So these two are now in parallel with each other, right? We can see that now. So mission accomplished, we can now add them. This was our 5. Now, the direction on this, and we'll do the value here in just a moment, but the direction on this is very important, and it's worth taking a pause to look at it. The direction generally can be found most kind of quickly by putting the direction of the arrow in whichever direction, let me rephrase, I'll get there. Have the direction of the arrow point up in this case, because the voltage source was negative on the bottom, positive on the top. That is to say, if the voltage source were like this, negative, positive, then the current source we would draw down. Okay? Remember that the current source, it produces a voltage as well. It forces a specific current, and it creates whatever voltage is necessary, so that this would be the orientation of the voltage that the current source creates. Therefore, this has the same orientation as that. If you had the arrow pointing down, you'd have the positive on the bottom and the negative on the top, and that wouldn't have the same orientation there. Okay? This is something that you get kind of used to doing the more examples you get under your belt. The current here we'll just say I equals, remember that's just Ohm's law that uses the voltage and the resistor there. So it's going to be the 10 over 5. It's going to be 2. So 2 amps right there. That's it. And then we can add those two together. They're in parallel. So copy this circuit down real quick. Keep putting that little extra circle there just for our reference. I'll square this up. That's my current source. That was a 2. Okay. We can go through here and label these terminal ends as well. Just, there's a lot of little circles flying around. There we go. This is our 3. And that resistor will be, looking around crazily for my calculator. That little resistor there is going to be the 15 and the 5. Remember that you want to do 15 inverse, 5 inverse, inverse. 3.75. Now remember, we want to get the Thevenin equivalent. So that's going to be this. We need a single voltage source and a single resistor in series. We're not there yet. Now, we could get there. Notice this is a current source in parallel with a resistor. Well, sometimes you just see what happens. See what happens if we source transform this. So if we source transform that, node A, 3, resistor, voltage source. B. Oh, I didn't draw the little circle there. There we go. So this will be the 3.75, and you see all we did there was we just took these two that are in parallel, smushed them together in a single line, and turned it into a voltage source. You may well be wondering, does it matter what order you write these? Can you put the voltage source there, the resistor there? Yeah, you can do that. Doesn't really matter where you put it. Okay, now so let me back up. Depends on exactly what you want to do. So it matters in the sense that it could change specific node values of voltage, right? If you move this voltage source, if you switch the locations of this voltage and the resistor, you'll change the value of the voltage at the node between them. But it won't affect like the current and the overall voltage between A and B, which is ultimately what we're concerned about when we're doing this kind of thing. The voltage here will just be the 2 times the 3.75, which will be something. So 3.75 times 2, 7.5. 7.5. There we go. And then these two guys are in series. I have A, B, 6.75, and this was the 7.5. So there you go. That's apparently the Thevenin equivalent. We have this, right? Voltage and resistor in series. So yeah, cool. So that's the Thevenin equivalent resistant circuit for this thing. The Norton equivalent then would have to be A, B, notice the arrow direction again matches up, and this would be I, oops, can't see me, you can't notice the arrow direction, there we go. Arrow direction is up, minus plus is upward. I is equal to 7.5 over 6.75. What a messy number. Let's check it out. 7.5 over 6.75. Oof, 1.111. That's probably enough ones. Yikes. All right. Yeah? Yeah, right on. Hang on just a second. All right, so let's check here so that we can kind of prove to ourselves that it works. We're going to go with a wire. Well, we'll do resistor. And we're just going to make the original circuit first. Voltage source, wire. Then we're going to do wire, wire, and there we go. We're going to go with a 3, 5. This was a 10. Remember, we always have to kind of make sure no number shows up there, but we can check down at the bottom right and see that it's a 10. And this guy was 15. There we go. Go ahead and slow the current down a little bit. There we go, right on. This was the original circuit, and then we will make our equivalent one. Remember, checking your results is important. There we go. Just making our equivalent one. This was 6.75 ohms, and this was 7.5. So you notice it says 6.8. It's just rounding for the display. It's not a big deal. If you look down at the bottom right, it says 6.75, so that's not an issue. And that's 7.5, so right on. So first thing to notice here when you're checking your answers for this is that nothing is happening in the equivalent one. So what you have to do is you have to actually make use of something across the terminals. So let's change it to like a 2. There we go, just to like get the current kind of moving through it a little bit. And it has to be the same thing, whatever it is, 2. And then all you do to check, hover over it, look down at the power, you can look at the current, you can look at the voltage, but I'll look at the current, 857.143 milliamps. And this one is 857.143 milliamps. Yeah, good. So it works out. So you see, by doing that, take them off here so that we can see it. We've changed this whole circuit, like this whole thing, into this. So pretty nice stuff. We can check out the Norton equivalent then as well. So kind of move these over, move those over. The resistor, oops. There we go. Resistor, go to draw, where's he at? Current source. There we go. And then connect them up. Connect them up. So you are going to get some movement here when you do the Norton equivalent. Just throw a whole bunch of ones in there. This was 6.75. So you're going to get some movement in there, but don't forget that you need to put this same resistor in there across the terminals because that's where you're looking at. You've turned your circuit into this. That isn't the circuit on its own. Don't check this one. You need to check this one. So that's really important. And 857.143. Yeah, right on. There you go. So that's all you got to do. All right. So now that we've shown how to check it and we've shown how to do, hang on, I'm trying to do too much at once here in my head. So now we've shown how to check your circuit. Let's talk about instances where you cannot get the Thevenin or Norton equivalent by just doing source transformation. So that's going to happen. That's going to happen an awful lot. In fact, that's probably going to happen most of the time. So what we can do is there's some procedure that we can follow. And we're not really going to do an example for this because we're going to have plenty of times to do examples of this later on. But we'll call this the steps to get Thevenin equivalent. Thevenin equivalent circuit. So these are the steps. There's two things that you need to get when you're trying to get the Thevenin. You need to get that resistor, and you need to get the voltage. So we'll do the resistor first. So to get the resistor, step 1, turn off all independent sources. That's step 1. Turn off all independent sources. So that means in order to turn them off, you can either keep drawing them, but just pretend that their values are 0. Easiest way for me is if you have a current source, remember that the current source, to turn that off, draw a little node symbol there. Turn your current source off. In order to have 0 current, it's just blank. Just get rid of it. For your voltage source, remember how to turn that off? The voltage source creates a voltage difference, right? How do we make sure that the voltage is the same? Good old wire. That's how you turn them off. Oh, arrow. That's how you turn them off. And it's going to be only the independent ones. 2. Determine equivalent resistance of circuit at terminals. Determine equivalent resistance. Don't know why I capitalized resistance of circuit at terminals. Okay, and we've done that, right? You know how to do that. Get your equivalent resistance. So if there are dependent sources, you've already turned off all the independent ones, but if there are dependent ones, so if there are dependent sources, you got a little bit more work that you have to do. You're going to find that you're going to need to put in either a current or voltage source and then calculate RTH. And it gets a little bit weird to explain, so the best way is with an example. And like I said, we'll see lots of those later. But just kind of really quick, if there are dependent sources, use a current or voltage source. Which one you pick doesn't really make a difference. Sometimes there can be an easier one that you could do just based off of source transformation. But in principle, it makes absolutely no difference. So use a current or voltage source and calculate RTH. So just kind of real quick to kind of show you what that would look like if we be a bit vague about it. Let's say this is a dependent voltage source, and it exists somewhere in a circuit that we want to equivalentize it. That's a technical term. And these are the two terminals, A and B. So since there's a dependent source there, what we will do is we will throw in this case, we'll throw in a current source, IS, throw in a current source. Now that current source, remember we just talked about, creates a voltage difference that will be plus and minus. According to this, it will be plus and minus that. And so we might call that VS, and we'll just symbolize that that's us measuring the voltage across those two terminals there, okay? It's not making VS, it's making the current, and VS is incidental, all right? Nevertheless, that must be in existence. Therefore, by Ohm's law, RTH is equal to VS by IS. And so that's how you would do that. Okay, like I said, it seems really weird, but we've already done an example. This is getting a bit longer than I'd expected it to, and we'll see loads of examples of this. So just go through the examples that we have later on, and you'll kind of see. So that's how you'll get RTH. Now you need VTH. So the Thevenin voltage, just one step for that. You're just going to calculate the open circuit voltage. Calculate open circuit voltage. That's just a fancy pants way of saying, just give me the voltage, man. Open circuit voltage, we can specify that that's across terminals. Across terminals. All right. Example. Not really an example, just kind of showing you what that looks like. Here's our circuit. Our mysterious circuit. Here's terminal A and B. And we're going to say, all right, plus minus VTH equals what? That's all you're going to do, right? You'll have like access to what this is, just like we did in our example, right? We had access to what this circuit was, and we asked ourselves, and we source transformed it. What we could have done also was we could have kind of looked at this and decided if we did nodal analysis or whatever, we could figure out what is the voltage difference across those two terminals there, and that would have been VTH. So that's all you got to do there. For steps to get the Norton equivalent, this will go to a new page. Pretty short, these steps to get the Norton equivalent. Steps to get Norton equivalent. Steps are shorter only because it's kind of the same thing. So obviously one of the steps would be get the Thevenin equivalent and then use source transformation to equivalentize those two together. But if you want to go straight for Norton, you can do that too. So that's the same. You can get the resistance the same. To get the Norton current source value, you're going to calculate the short circuit current across the terminals. Calculate the short circuit current across terminals. So remember I said that it would be important, the idea of using a wire. Well, here it comes. So we have our circuit. I'm going to do the box first. Yeah, there we go. That was enormous. Okay, so we have our circuit, whatever that is. We're just going to do a wire. IN equals what? The arrow there, just like usual, totally up to you, okay? We arbitrarily defined this as the direction of our IN that we are going to attempt to calculate. Could just as easily have it point up. It makes absolutely no real difference. Remember that we can do this because the Norton circuit is this. The Norton equivalent circus will be this, right? Put a TH there, or N, doesn't really matter. It will be this, and if we put that wire in there, this gets bypassed, the current goes all the way around like this, and would be going down in this case. So that's how it is that we're able to do that. Please make sure you look at some of the examples. They're totally going to help you out, hopefully. And good luck.